We just talked about the different carbon content for the different types of coal. And I can actually show them to you right now. For instance, here you can see the type of coal called lignite, which is still very much almost looks like charcoal wood. And it's actually not far from the peat, which is literally just dried swamp material. So this has maybe 50% carbon or so, but as it gets compressed, the carbon content goes up to lignite and then up to bituminous coal. I can feel the heft of it. It's a little bit heavier here. It's got a higher carbon content. It's denser. And then finally to the metamorphosed coal that we call this anthracite. It's only about 3% of all coal, but it's the cleanest and the most useful in terms of energy per pound. But really, the whole point with burning coal is that you are taking advantage of the chemical energy that's trapped within the molecules of the material, and burning anything would work. I mean, on average, coal gives you about 28 gigajoules per ton. But you know, if I take the wood of this cutting board here or a stack of newspapers and magazines, it's about half that, sort of 14 to 17 gigajoules per ton. You just need twice as much, and it's not as convenient. I can go to one place in the world and just dig up coal out of the seam. I have to chop down a lot of trees to get the same amount of energy. You can just pick up leaves and grass, but this only gives you about 4 gigajoules per ton. So again, the choice of coal has simply been, it's a fairly high energy density compared to other forms of biomass, and there's a lot of it around. Now, I can demonstrate to you what the energy content is in biomass. And what I have here is a jar full of hazelnuts, and I've taken one of them and I've put it here on this stand. I've put one hazelnut at the end of a needle there, and what I can do is take this beaker of water. I've got 250 milliliters of water here. And I've got a thermal probe here, which currently is telling me that the temperature of the water is 20.6 degrees Celsius. What I want to do is light this hazelnut on fire, put the cup of water on top, and then once the hazelnut is entirely burned, measure the final temperature of the water. Now again, we talked earlier about the conservation of energy. If there's energy in here and then I burn it, where does that energy go? Well, it goes into the heat of the flame. And that flame will heat up the water, and I should be able to calculate how many calories are in that one hazelnut. So let's take our lighter and light the hazelnut here. It's going to take me a moment with all the oils that are in the hazelnut to get this thing actually burning. And once I get this going, I can take the lighter away and I'll put the water on top. Now it'll take a little while for this to burn. And so you can see it's starting to smoke here. And in just a moment, I'll have this going enough that I can now take the lighter away. And I will take my beaker of water and put it on top. And I will now measure the degree to which the water here increases as this hazelnut burns entirely. In fact, I can already see the temperature is rapidly increasing. It's already up to 22 degrees and on its way up. What I need to do is wait until this hazelnut burns entirely for me to understand exactly where that energy went. So our hazelnut is pretty much burned all the way through at this point. What I want to do now is read the temperature of the water and see how much that temperature has gone up. Remember, we started at 20.6 degrees. The temperature now reads 31.7 degrees. So we've actually increased the temperature of the water quite a bit by burning just this one hazelnut. And what I'll have you do now is calculate from this information how much water it was. Remember, it was 250 milliliters, and what the difference in temperature was between the starting and ending points.